For the first time in recorded history, humanity witnessed the arrival of an object from beyond the boundaries of our solar system. This celestial visitor, later named Oumuamua, captivated astronomers and forever altered the direction of space exploration. Until its appearance, astronomical efforts had largely centered on understanding our own solar neighborhood. Probes were launched toward nearby planets, moons were scrutinized, and asteroids were monitored with increasing precision. However, Oumuamua changed all that. Detected by the Pan-STARRS-1 telescope in October 2017, this enigmatic object ushered in a new era in the study of interstellar phenomena. The nature of Oumuamua immediately sparked worldwide scientific interest. In an effort to understand its composition and origins, the James Webb Space Telescope, JWST, was later tasked with capturing detailed infrared imagery of the object. These images revealed several unprecedented features, offering insights that had never been obtained from any known asteroid or comet. The name Oumuamua is derived from Hawaiian, meaning first messenger or scout. It fittingly signifies its pioneering role as a herald from the stars. The Pan-STARRS-1 telescope, perched on the summit of Haleakala in Maui, was the first to detect the object. What made it especially unusual was its elongated, cigar-like shape, a stark contrast to the typically round or irregular forms of known comets and asteroids. Traveling at immense speed through the inner solar system, Oumuamua's trajectory indicated it was not gravitationally bound to the Sun. Its brief passage marked a transient visit from a domain far beyond Pluto. The object's strange shape and acceleration posed significant classification challenges. Initially labeled as an asteroid due to the absence of a visible tail, it later exhibited an unexpected increase in velocity, suggesting the influence of forces other than gravity. This unexpected acceleration ignited fierce debate. Some scientists proposed that solar radiation pressure acting on a thin, reflective surface could explain the object's motion. Others speculated more exotically. Could Oumuamua be an artificial probe sent by an advanced civilization? Though the majority leaned toward natural explanations, the mere possibility of a non-natural origin renewed enthusiasm for studying interstellar bodies. The urgency to gather data was palpable. With only an estimated 11 days of high visibility before Oumuamua drifted out of range for Earth-based telescopes, global observatories mobilized rapidly. Facilities such as the Very Large Telescope in Chile collected data on its spectral color, light reflectance, shape, and trajectory. These observations showed a reddish hue, hinting at prolonged exposure to cosmic radiation, unlike surfaces typical of local solar system objects. Each bit of data refined models attempting to explain Oumuamua's makeup and origin. Theories emerged. Perhaps it was a fragment ejected from a shattered world in a distant star system, or an icy shard expelled by tidal forces near a massive celestial body. Some models even considered exotic physics or speculative alien technologies. To pursue deeper analysis, astronomers turned to the unparalleled capabilities of the JWST. Its advanced infrared sensors were ideal for analyzing faint heat emissions, measuring surface composition, and understanding the material structure of rogue interstellar visitors. With high-resolution imaging, JWST uncovered the object's thermal properties, rough surface, and internal composition. This data ruled out certain theories and supported others, though Oumuamua still defied full explanation. The discovery began with Pan-STARRS-1, an innovative telescope equipped with a 1.8-meter mirror and a massive 1.4 gigapixel camera. Positioned to capture expansive swaths of the night sky, it routinely scans for moving objects such as asteroids, comets, and supernovae. Operating from the Haleakala Observatory, the telescope is part of a larger effort to detect near-Earth objects, NEOs, that might pose future threats. Pan-STARRS-1 systematically compares nightly images to a database of known stars and objects. Any anomaly, a slight movement, or variation in brightness, triggers a follow-up analysis. Through this method, it has cataloged millions of celestial bodies, enhancing both planetary defense strategies and our knowledge of small solar system objects. Its strength lies in identifying fast-moving or fleeting phenomena, like Oumuamua. The object's rapid movement, lack of tail, An eccentric trajectory distinguished it from typical space rocks. The telescope wasn't built to search for interstellar visitors, but its wide-angle survey design made it capable of catching such unexpected anomalies. On the day of its discovery, astronomers recognized that the object moved too swiftly and followed a path too eccentric to originate from our solar system. Unlike the elliptical or circular orbits of most solar system objects, Oumuamua traveled along a hyperbolic path, indicating it was on a one-time pass through the inner solar system. Once it rounded the Sun, it began to accelerate away, bound for the depths of interstellar space, never to return. This chance discovery underscored a critical principle. By scanning the entire sky regularly and methodically, scientists can detect the unknown. The Pan-STARRS telescope, though designed for planetary defense, revealed its broader potential for discovery. The accidental nature of the event emphasized how preparedness and wide-angle vigilance can yield transformative scientific breakthroughs. The naming of Oumuamua was both poetic and fitting. It suggested a forerunner, a cosmic scout possibly hinting at other similar visitors. Its detection prompted scientists to consider how frequently such objects might enter our solar domain. Perhaps Oumuamua was not a rare fluke, but one of many undetected interstellar travelers. If so, how could we better find them? And could we intercept them? These questions energized the scientific community. The short observational window for Oumuamua prompted discussions about how to track and study future interstellar objects more effectively. The realization dawned that with quicker detection and faster spacecraft, we might one day send missions to intercept and study these cosmic messengers firsthand. While Pan-STARRS 1 continues its nightly scans, the legacy of Oumuamua has inspired global efforts to enhance our detection capabilities. Future telescopes, such as the Vera Rubin Observatory, will use large-scale sky surveys to identify thousands of moving objects nightly. This will significantly improve our chances of spotting interstellar visitors early enough for meaningful study. In parallel, astronomers continue leveraging JWST's infrared capabilities to examine similar phenomena. Its sensitivity to thermal signatures makes it an ideal tool for distinguishing between icy, rocky, and organic materials in space. When combined with rapid detection systems, JWST can be used for immediate analysis of any new interstellar object. The unique motion, reddish spectrum, and unexplained acceleration of Oumuamua redefined how scientists evaluate mysterious cosmic phenomena. Whether composed of exotic ices, compacted rock, or engineered materials, its behavior challenged conventional physics and invited bold theories. Though the majority consensus remains rooted in natural explanations, Oumuamua sparked renewed interest in the search for technosignatures and alien artifacts. It also rekindled public fascination. The idea of receiving a visitor from another star system tapped into a deep cultural curiosity. Was this just a rock? Or a vessel? What stories could it tell about its place of origin? Meanwhile, agencies and institutions began drafting mission proposals to send spacecraft in pursuit of future interstellar objects. Concepts such as solar sail-powered interceptors, rapid response probes, and deep space CubeSats are being seriously considered. These missions would seek to rendezvous with such objects, collect material samples, and even return them to Earth for detailed analysis. Efforts are also underway to revisit old telescope data. Astronomers are combing archives, searching for anomalies that might represent previously unnoticed interstellar visitors. Improved algorithms and machine learning tools are helping sift through terabytes of data, possibly uncovering a history of cosmic visitors hidden in plain sight. The implications of Oumuamua's visit are truly far-reaching, signaling a major shift in our understanding of the solar system's place within the larger universe. For centuries, our scientific models operated under the assumption that the solar system was largely isolated, with the Sun and its orbiting planets forming a self-contained neighborhood. But the sudden appearance of Oumuamua in 2017 shattered that notion, serving as tangible proof that our solar system is not a closed environment. Rather, it exists as part of a dynamic, interconnected galactic ecosystem, one in which material from distant star systems can travel across immense stretches of space and make brief but significant appearances in our cosmic backyard. This revelation carries profound consequences. It means that the gravitational interactions, stellar outflows, and planetary disturbances in far-off systems are not just localized phenomena. They can fling debris, icy fragments, or even rocky objects like Oumuamua into interstellar space, where they travel silently for millions or even billions of years. Eventually, some of these ancient wanderers cross into the domains of other stars, such as our Sun. When they do, they carry with them the fingerprints of their origin, clues etched into their surface chemistry, structure, and motion. By studying them, we get a chance to peer into the history of worlds far beyond our own. Each interstellar object like Oumuamua is more than just a rock flying through space. It is a relic, a physical artifact from a completely different planetary system. It may have once been part of a planet, moon, or asteroid belt orbiting a foreign star. By examining its physical properties, such as its shape, coloration, trajectory, and acceleration, scientists can begin to reverse engineer the conditions of its home system. What kind of star ejected it? Was it the result of a planetary collision, gravitational slingshot, or stellar explosion? And what materials is it composed of? Could it harbor organic compounds or water ice, offering hints at the building blocks of life in other parts of the galaxy? This insight is particularly compelling when considering the possibility of panspermia, the hypothesis that life could be spread across the universe by traveling cosmic bodies. If interstellar objects contain the molecular ingredients necessary for life, or were even ejected from life-bearing environments, their journeys could represent more than random motion. They could be the vehicles of cosmic evolution. While this remains speculative, the fact that material from other star systems is capable of entering ours makes such scenarios scientifically plausible. Ultimately, Oumuamua's fleeting visit has had a lasting impact. It has opened our eyes to the active, shared nature of the galaxy and inspired new methods of detection and study. It reminded us that we are not alone in the universe, not necessarily in terms of intelligence, but in the broader sense that we are part of a galaxy teeming with motion, exchange, and potential. In every interstellar object lies a story untold, waiting to be heard by the instruments and minds prepared to listen. Pan-STARRS 1 and JWST exemplify the complementary tools of modern astronomy. The former scans the heavens for the unknown. The latter probes the known with exquisite detail. Together, they offer a powerful framework for the emerging field of interstellar object science. Oumuamua was not merely a celestial oddity. It marked a turning point, reminding us that our view of the universe is still expanding. It invited humility and curiosity, showing that cosmic surprises await even in familiar skies. As new technologies emerge and next-generation telescopes come online, humanity stands poised to continue exploring these strange visitors. Ultimately, the legacy of Oumuamua is one of inspiration. It proved that our tools are sharp enough, our minds curious enough, and our sky surveys wide enough to detect interstellar messengers. With continued investment in space observatories, detection systems, and mission planning, the next interstellar object may not just be observed from afar, but visited, studied, and understood.